Dr. Luo, and he is currently an associate professor in the Department of Mechanical Engineering. He obtained his PhD at the Royal Institute of Technology in Sweden, after which he worked as a postdoctoral fellow, first at Karlsruhe University in Germany, after which he also worked as a research associate at the Rensselaer Polytechnic Institute in upstate New York. And basically his research interests are broad, but focused mostly on finite element methods and computational biomechanics. His work is supported by a number of funding sources, I believe, including NSERC, the Manitoba Health Research Council, or I guess Research Manitoba, sorry, and the Manitoba Medical Services Foundation, just to name a few. He's authored approximately 100 publications, including several book chapters, articles in international peer-reviewed journals, and a number of conference proceedings. And so today we're very much looking forward to hearing about his work.
Okay, thank you very much for your introduction. And good afternoon, welcome to this presentation. So in this presentation, I'm talking about our research work in our group. It's around centered on this image-based computational biomechanics. I will talk about our recent progress and the challenges we are facing. Okay. So first, I will introduce you to image-based computational biomechanics. Then I will present these three progresses in our group, and I'll talk about challenges. Maybe I don't have enough time to cover all those three subjects, so in that case I will briefly introduce the last two. Okay. So. First one, what is image-based? In the introduction, I will first introduce what is image-based computational biomechanics and biofidelity in computational biomechanics. Okay. So, what is image-based computational biomechanics? From the title, we can see that the three components. Okay. So actually, the image-based computational biomechanics is an emerging research area that integrates three components. Okay, the first one is biomechanics, conventional biomechanics. The second one is engineering computational methods, and the third one is medical imaging techniques. Okay, now let's take a look. One by one, what is the role of each of the components in this image-based computational biomechanics? So first, what is biomechanics? The definition given by Dr. Feng is biomechanics is mechanics applied to biology. It's a very general area, okay? And biomechanics also seeks to understand the mechanics of living systems. Okay? And Dr. Feng is generally believed the founder of modern biomechanics. Okay? And biomechanics is a young subject, but it has a root that can be traced back to ancient Greek. Okay? A book by Aristotle, and also can be traced back to an ancient Chinese medicine book. It's called Lei Jin. Okay, it's very famous in China. Okay, biomechanics, as you can see from the definition, biomechanics covers a very wide territory. Okay, so from human being to animal plants, and from the human body to organs to cells to tissues, etc. Okay. So in computational, in image-based computational biomechanics, what we need is the theoretical framework from biomechanics that include the classic actually biomechanics is based on classical mechanics. Okay, and of course biomechanics has its specialties that include musculoskeletal kinematics and dynamics, and circulation and fluid mechanics, tissue properties. Okay, so that is another very special aspect of biomechanics. So tissue material properties are very different from engineering materials. Okay. So obviously biomechanics is the theoretical base of image-based computational biomechanics. Basically what we use is the governing equations established in biomechanics. Okay. Then the second component is engineering computational methods. Okay. The following methods have been used in computational biomechanics, include Van method, computational multiple dynamics, computational fluid dynamics, etc., etc. Okay, that include only other methods. So the role of computational methods in the image-based computational biomechanics is that they are necessary tools for solving the governing equations established in biomechanics. So those governing equations are very complex. We cannot obtain the analytical or explicit solutions. Okay, so these numerical tools is quite necessary. And then the third component in the image-based computational biomechanics is medical imaging techniques. Okay? So we have a number of modern imaging modalities, including MRI, CT, and other modalities. We basically use this MRI and CT, and also this motion capture system. So what is the role of imaging in this subject? These modern medical imaging techniques are able to create precise three-dimensional representations of the interior anatomical structures of human body. Okay, so all otherwise cannot be seen, right? Okay, and those information include the geometrical information, the shape of sizes, and material information that captured in the images can be used to constructing biomechanical models. Okay. So one contribution by this medical images, is that the biofidelity. I will talk a little bit more about what is biofidelity later. Biofidelity can be greatly improved by using medical images. And the biofidelity has been a major obstacle preventing computational biomechanics to solve practical problems. So everybody, if you do numerical modeling or computer modeling, the first thing you need to do is that make the model similar to the real object. Otherwise, the simulation results will not be reliable, right? Okay, so the major roles of image-based computational biomechanics in bioengineering and in clinic applications include the following aspects. The first one is to help understand pathophysiology of injuries and diseases. Okay, so it is believed all the phenomena happening in the human body is somehow more or less related to mechanics. Okay, for example, split of cells. Okay, and second role is the customized design of implant, prosthesis, arthroplasty. Okay, so all those are related to engineering design and the mechanics. Okay, the third one is orthopedic surgery planning and verification. Okay. So there are many applications by other groups or researchers over the world, okay, using the image-based computational biomechanics. Several examples are given here. Head injury, orthodontics, spine injury and disease, joint injury, and homemade joints, and heart, and blood circulation, etc., etc. Okay, there are many more. The list is quite long here, and there's common issue in those applications. That is the model biofidelity. Okay, so what is model biofidelity? Biofidelity is the resemblance or similarity of a biomechanical model to the original object, for example, the human body. Okay? And good biofidelity is crucial in applying computational biomechanics to understand biological, biomechanical phenomena and to address patient-specific health problems. Okay? So it's very important. Then, what aspects biofidelity include? So mainly, biofidelity or biomechanical model may include three aspects. The first one, geometry. Second one is material, and the third one is loading constraint conditions. So if you in the field of fundamental method, then you know that these three categories of parameters are required in the simulation as input, right? Okay. So if you do numerical modeling, if the input is not accurate, then the output, the result, cannot be accurate, right? So any inaccuracy in the above aspect will affect the final results. Okay, so that's why biofidelity is so important in computational biomechanics. And medical imaging has offered an effective way to improve about biofidelity. Okay, I'll talk one by one in the following. The first one is geometric biofidelity. Okay, so geometric biofidelity means the similarity of the biomechanical model to the original subject in geometric shape, in dimensions, in sizes. Okay. So in the last decades or so, the geometrical biofidelity of mechanical models has been greatly improved by using medical images. For example, the generation of final meshes from medical images. So you can see here is one example of the final mesh generated from medical images. So before that, they have to draw some figures and then generate the mesh. There are always some errors or difference between the final model and the actual object. So the second aspect of the biofidelity is material biofidelity. That is the similarity of biomechanical model to the original subject in the material properties. Everyone knows this biological tissues are very complex in the properties. Okay, they are inhomogeneous, viscoelastic, anisotropic, and they're very challenging to simulate. Okay. However, tissue information captured in medical images is very helpful for implement or assign material properties in biomechanical models. For example, fundamental model. Okay, if you use mimics, okay, so the inhomogeneous material properties can be assigned in an accurate way, but based on medical images. Okay, the third aspect of biofidelity is the loading constrained conditions. That is the similarity of the biomechanical model to the real-world biomechanical problem in loading constrained conditions. Obtaining these kinematic variables and impact force are carrying a real world accident, for example, falling, is very challenging. Okay, they come from several aspects. The accident occurred by accident, not by a plane, right? So there's very little information can be obtained from the real world accident. However, we can use the motion pictures captured by the high-speed cameras to retrieve the loading constrained conditions in studies, not in real-world accident. Okay. Okay, those are the introduction about the image-based computational biomechanics. Now, the following, I'll talk about the progress in our group. So the first progress is in head injury analysis and helmet design. In this part, I will first talk about sports-related head injuries, and then I will introduce our work in constructing image-based fundament head model and use the model to study the mechanisms of head injury, and then use that this model to improve helmet design. Okay. So head injury is quite popular, quite common in sports. Okay. So based on some clinical statistics, for example, from this American Association of Neurological Surgeons, okay, about 450,000 sports-related head injuries occurred in the US in 2009, and most of those head injuries are mild head injuries. That means maybe you're not bleeding from outside. Okay. So everybody should hear about this concussion. That is kind of mild head injury. Okay. So I will talk about the classification of head injury later. And the top category of sports-related head injuries are cycling, baseball, football, soccer, basketball, etc., etc. Okay. In Canada, this ice hockey is a major source of head injury. Okay. Both their collisions, also their fightings. So that's very easy to cause head injury. And people may ask, sport helmet has been used in protecting the athletes for many years, but why the incidence of head injury is still high? Okay, so why the helmet is not effective in protecting people from head injury in the sports field? So head injury actually can be classified into two major categories. The first one is open head injury. That means the skull, the heart bone has been broken and the brain tissue may be penetrated. Okay, so that is open head injury. The second category is closed head injury. So the skull is still okay, not broken, but the brain tissue has been damaged. Okay, so most of the head injury happening in the sports field belong to the second category. Okay, and clinical data have shown that helmet is more effective to prevent the open head injuries, but much less effective in reducing closed head injuries, such as concussion. Okay, so If you wear a helmet, that does not mean you can be free from concussion. Okay? So our study was focused on closed head injury. Okay? The reason is that it has high incidence among head injuries, especially in sports. Okay? And then it's preventable. And the impact force, because the impact force is usually relatively low compared with the head injury with open scalp, okay, the scalp is damaged. And then the third reason is that high cost is required for hospitalization, care, and rehabilitation. So our first step in this study is to construct a reliable fundamental head model with high biofidelity. Okay, so we start constructing the model from a set of CT scans. Okay, so one sample CT scan is shown here: the sagittal view, axial view, and the coronal view. So in the construction, we extract material information first from the medical imaging. Okay, so that is used to assign the material properties in the model. And the second aspect is we extract the geometrical information from the medical images and obtain a geometrical model of the head. And the third one is that we use motion picture to retrieve the loading, excitation, and boundary conditions for the head. Okay? And then combine those information, we construct the fundamental model. And one thing I want to stress here is the material properties. In the establishing the material, in assigning material properties, we first correlate the tissue density to the CT number or Hounsfield unit in the CT images. Okay, so here rho is the tissue density, and the CT is the CT number in the CT scan. AB are experimentally determine their coefficients, and then the second step is to correlate tissue mechanical properties. For example, Young's modulus to the tissue density. Okay, so here is Young's modulus, rho is the tissue density, alpha, beta, again experiment determine the coefficients. Okay, what's showing here is the distribution of the Young's modulus in the fundamental head model. So we then validate the fundamental head model by experiment results reported in the literature. We didn't have condition to conduct this experiment by ourselves. Okay, so you can see reasonable agreement can be observed from the comparison. Of course, there's some difference there, but there's a reason because the cadaver used in the experiment and the CT scan used in our modeling are not from the same subject. So there's some differences in the result. Okay, and then we applied the model to did a number of things. First, we investigate the conjugal brain injury, okay, and then we studied the role of cerebrospinal fluid and intracranial pressure in protecting the brain. Okay, and then we use the model to improve helmet design. So, conjugal brain injury is quite special. The reason is that here is one case of this brain injury. So here, that is the impact site and this is the opposite side to the impact side. Okay, you can see that of course there's bruise or damage on the impact side. At the same time, there is another damage on the opposite side of the impact. Okay, so it's not straightforward. I mean, the reason is not straightforward. Okay, we use our model to study this kind of brain injury. Okay, here I just jump to the conclusion. Okay, so fundamental study results shed some light into the mechanical mechanism involved in this kind of brain injury. And we found that this kind of brain injury is a combination or is combined result of brain tissue oscillation, okay, collision with the hard skull and the wave superposition. Okay, it's quite complex. So here I have an animation. That is one cross section, axial cross section from the head. Okay, so suppose we apply a impact here, and then let's take a look at the strain variation or strain history in the brain tissue. Okay, so at the beginning you can see the large strain occur at the impact site. Okay. And then after a certain time, the large strain occur on the opposite side. Okay, and then there is oscillation of the brain tissue. Okay, to both sides. And we try to find out the condition for the wave superposition. It's very difficult. Okay, we try to find a condition that means for a certain geometry, when a certain impact, then the incident wave is superposed with the refracted wave, and then they have the same phase. Okay, in that case, the mechanical energy will be amplified. Okay, that means the damage could be severe on the contractile side. Okay, next we use the model to investigate the role of cerebral spinal fluid. Okay, that is a fluid in the brain. Okay, it's similar to the water. But there's some proteins in the fluid, okay? And also in the whole head, there's a pressure, okay? It's called intracranial pressure. It's produced by this fluid. So we investigate these two biological, physiological parameters on head injury. Okay, so for this purpose, we establish 3 fundamental models and treat this fluid differently. Okay, this is the only difference among the 3 models. The first model is that the fluid is considered as solid material. Okay, and second model, we treat the CSF as a fluid, but without pressure. Okay, the third one is the real one. Okay, it treats as a fluid with the normal intracranial pressure. So I jump over the results and come to the findings. So we found from the results that cerebral spinal fluid and intracranial pressure play important roles in protecting our brain. Okay, so the the cerebrospinal fluid absorbs most of the mechanical energy induced by impact. Of course, it's moderate impact, cannot be very large, okay? Which otherwise would be all transferred to the brain tissue. Okay? So our study have shown that about 35% of the mechanical energy has been absorbed by the cerebrospinal fluid. Okay? So that's quite significant. And the second finding is that if there's no intracranial pressure, then the level of stress produced by the impact in the brain tissue would be significantly higher. So our results show that if there's no intracranial pressure, then the strains in the brain tissue will be 50% higher. Again, it's very significant. Okay? Okay, next I'd like to talk about a little bit about the integrated head injury analysis and helmet design. So first I will review the issues in the current practice, and then I will introduce our proposed method for subject-specific helmet design, and then we use the model to do some parametric studies. So what is the issue in the current practice? Okay, the first one is that the helmet does not fit perfect. Okay, if you go to a store, a sports store, you cannot find a helmet that perfectly fits your head, right? So this, if the helmet does not fit, it cannot protect you in the maximum effect. Okay. The second one is that accelerations has been used as a criteria. Okay, the whole head has one acceleration, but only some of the brain tissue is damaged. Why? Because of the stresses distribution. They are inhomogeneous in the brain tissue, right? Okay. And in the current design process, the focus is on the helmet, not on the brain tissue. Because what damage is the brain tissue, right? Not the helmet, right? So the focus is on the wrong place. And the most important one is that there's no immediate direct feedback information for us to improve the helmet design. Because if we want to improve the design, we need to have feedback information. Otherwise, there's no way to improve it, right? Okay? And the issues in the helmet testing is that we mostly use the in vitro catheter test because it's not allowed by the ethics to test with the UV people, right? And of course, there's some in-field test, but there's no stress strain information about the brain tissues, right? So those are the issues. Now, our strategy to improve the design is that we're not expecting that the helmet design can protect you from any head injury. That's not possible, right? But we should maximize the protection effect by using the available materials and manufacturing technologies, right? And to protect the subject from cross-head injury, we should reduce the strains, intracranial pressure introduced by impact as much as possible, because those parameters are believed related to the damage of brain tissue. Okay? And the final strategy is that we are going to provide immediate feedback by virtual impact test. Okay, so if you have the impact, the feedback information, then it's possible to improve the design. So the procedures shown here. We start from a set of medical imaging. Okay, and by following the procedure I introduced before, we construct first a head model. Okay, this head model include interior anatomic structures of the head. Okay, for example, blood vessels, white matter, gray matter, etc., etc. Okay, it depends on the resolution of the macular image. Okay, we try to include as much as possible, and then we start design the helmet for this subject. The process is very simple. We extract the outermost shell of this model and use that to construct the soft pad in the helmet. Okay, and then we expand this geometrical surface to obtain the shell, the hard shell. Okay, and then we combine them together, we obtain the helmet, and then we put this one with the head, we obtain a head helmet system. Okay, so now we have the model, and the advantage of this model is that it's subject-specific design, because the geometrical information are extracted from the medical image of the subject. The second advantage is that this model includes the interior anatomic structure, okay, for studying head injury. Okay, now and then we use this model we just obtained to conduct a number of parametric studies that include the effect of helmeted with non-helmeted, okay? The effect of shell stiffness and strength, and the effect of platform compliance and platform thickness. So all those parameters, the last three, are very important parameters in the design of the helmet. Okay. So I just jumped over the results and to the conclusions. So a helmet is able to reduce impact-induced maximum peak intracranial pressure. First, it can reduce the intracranial pressure induced by impact. Okay. Also, it can reduce the maximum peak strength in the brain tissue. Okay. Depends on the situation. I didn't provide numbers here because it depends on the number of parameters, the prime load. And second finding is that if the helmet shell has adequate strength to resist penetration, then if you increase the shell stiffness and strength further, it will not help protect the brain. Okay, there's a limit. Okay, actually, if the stiffness is too high, it can have adverse effect. Okay, and then the helmet platform must have an appropriate stiffness. So too stiff or too soft pad would not provide maximum protection. So in the design of sport helmet, the select of this platform is really, really important. So if you go to a sport shop, buy a helmet, if the helmet is expensive, it's not because the shell has high strength, it's because of the platform. It's a very good performance. Okay? And of course, increasing the foam pad thickness is most effective to reduce head injury. But we know that the thickness cannot be as large as you like, right? Okay, so that is first progress I hope I can finish it. Okay, second progress is the prediction of impact force inducing accident force. Actually, this research project is still going on. Okay, so what I put here some preliminary results. So why we need to develop a model to predict the impact force in fall? The reason is that accident fall has been identified the main cause of bone fracture for old people. Okay? And the reason is that the impact force induced in fall is quite high and that can readily exceed the strength of the bone. Okay? However, the impact force induced in fall is subject dependent. That means higher person, fat person, when they fall, the impact force will be different from a shorter person, thinner person. Okay? So the impact force is different. And dynamic simulation is the only practical way to predict the impact force for old people. You cannot do any experiment to old people. Okay? However, to assess hip fracture risk, we do need the impact force. Okay? So our solution is that we construct dynamic model, whole body dynamics model from the whole body DXC image. Okay? Because the reason is that the image capture the mass distribution information in the whole body. Okay? So that information is adequate for us to construct a dynamics model. Okay? For example, calculate the mass of a segment, the mass center of a segment, mass moment of inertia, right? All those are required in dynamics model. Okay, we construct swinging dynamics model. Use the medical image. And then it was used to simulate a sideways fall to predict impact force. The sideways fall is believed the most dangerous scenario for older people for two reasons. One is that there's very little protection in the sideways direction, and then the second one is that very little soft tissue cover the head. Okay. So the full process is split into two stages. The before landing, okay? The stage before landing and the stage of landing. That means the contact of the body with the ground. And the two stages are governed by the Lagrange equation and the equation of damped-free vibration. Okay, here this mass is so-called effective mass. And then we validate this model by controlled and protected full test use young volunteers. Okay, so the procedure is like this. We first, EVG, scan this subject, the experiment subject, and obtain the DXC image, and we use DXC image to construct the dynamics model. So the dynamics model is subject specific. It is this guy's dynamics model. Okay, and then we use the dynamic model to predict the impact force. Okay, at the same time, we use this subject to do the experiment. And in this experiment, there is a force sensor under this pad. So the impact force is recorded in the experiment. Okay? And then we compare the experimentally recorded result with the predicted impact force. Okay? We compare the hip position, hip vertical velocity, and the impact force. So you can see the experiment and prediction have quite good agreement with each other. And then we use the model to do some parametric study to figure out what factors affect the impact force. Those factors include the body weight, height, body mass index, etc., etc. Okay, we totally will obtain 80 clinical DXA images used in this study. Okay, and then we found that. Okay, conclusions from this part of study. Subject-specific dynamics modeling is much more accurate than conventional methods in predicting the impact force. So the relative error compared to experiment results was reduced from 30 to 40% to 9%. So the improvement is significant. However, there's still space to improve. Okay? Another finding is that the impact force is not only affected by anthropometric parameters such as body weight, body height, BMI, but it's also affected by the body configuration just before landing. That is very complex because it's difficult to describe the configuration before landing. Okay, so therefore the empirical functions established by experiments are not accurate in estimating the impact force. Okay. So I only have 10 minutes, so I just skip this part. Okay, I jump to the challenges. Okay, there's still many challenges in image-based computational biomechanics, although progresses have been made. Okay, not just in our group, also in other groups, by other researchers. Okay, and we have identified a number of challenges from our research work. Okay, that include biofidelity again, and the mechanical characterization of biotissues and multi-scale modeling. Okay, let's take a look at biofidelity. I just said that image-based computational biomechanics offer a great chance, a way to improve biofidelity, but still we have a long way to go. Okay, my opinion is that achieving 100% fidelity is very difficult, if not impossible. Okay, because this human body is a live organism, right? And another reason is that improvement of biofidelities also depend on progress in other fields of biomechanics. For example, mechanical characterization of tissues. Okay, that is a very complicated area. And there are main challenges in accurately characterizing tissues by mechanical tests. The reasons include tissues are heterogeneous, okay, anisotropic, etc., etc. They have very complicated mechanical properties. And tissue mechanical properties are also affected by a number of factors, okay, age, gender, race, health status, physical activities, etc., etc. All of them affect the tissue mechanical property. For example, bone strength, right? And another reason, it's not clear how tissue compositions affect tissue mechanical properties. So in current modeling, here I provide the bone chemical composition. A bone contains mineral phase, okay, organic phase, water. So in current practice modeling, we only consider this one in the model, in the mechanical properties of bone. Okay, so is there any effect from other phase? For example, the organic phase. Is there any? How about the collagen type 1? Will that affect the bone strength? The answer is yes, but we don't know how. Okay. Okay, the another challenge is multi-scale modeling. That is necessary, okay, to understand causalities occurring at different scale level, but it's very challenging. Okay, an effective and reliable multi-scale modeling method has not been developed in either direction. Okay, upward, downward. That means from home body to molecules, or from molecules to the home body. Okay. One example is given here. So we have, I just talked about concussion. Okay. So two players have a collision, and there's mechanical energy introduced, right? By this kinetic energy, velocities. Okay. So this mechanical energy is transferred from the body level. Okay. This mechanical energy, of course, relates to the velocity of the two players and their body masses, etc., etc. Right? Okay. So this mechanical energy is transferred through a helmet, okay, and then to the brain tissue, and then somehow break a axon, okay, and cause concussion. So how this energy is transferred from body level to this axon is not clear. Okay. So there is one, and we need to use the multi-scale modeling to figure out this. And another example, okay, modern medical imaging techniques have shown that there is big difference between non-osteoporotic bone and osteoporotic bone. Okay, so you can see this that visually they're different. Okay, however, we don't know how the microstructural parameters, for example, the trabecular network topology, porosity, okay, plate road sizes, dimensions, etc. How those parameters affect the bone strength. Okay. Okay. Finally, I want to thank my research group and my research collaborators and my research sponsors. Okay. Thank you. Thank you very much.
That was an interesting talk. I'm guessing there will probably be a few questions, and we do have a couple minutes. So, anybody want to? Zara?
Yes. Hi. First of all, thank you. Am I correct to assume that despite all the challenges that you mentioned, you're using your finite element modeling, you can have a relatively correct, accurate model, person-specific model?
Sorry, what's your question?
My question is, am I correct to assume that you can have your model for one individual to be relatively accurate?
Yes, compared with the conventional way to construct the model.
Then next, the main question is, why don't you print the element? If you have the model, why don't you print it?
That's possible, yes, but the material property is not the same. That's the main issue. The material property. For example, the bone. Okay, I can use 3D printing to print out the bone. Okay, for example, from the medical image, right? But the material used in the printing is different. It's very different from the material property.
With the advancement in 3D printing, it is conceivable to assume that perhaps we can even, I mean, that is advancing much more rapidly than any
Yes,
other
yes,
games.
it's possible. This
Then
is
probably they can have much better helmets for professional hockey players, professional boxers.
right. If that's exactly what we propose, yes.
Are
Yeah.
you collaborating with OIC for that?
No, number years ago. Because that's for the project related to the head injury was completed, I think, 2 years ago.
I can connect you to them. I have an engage if one of your students turns to BME.
Okay.
Right.
Thank you. But the printing of the helmet with the 3D printer is attractive idea. However, at this moment, it's too expensive. Right.
Well, professional hockey players make money.
Maybe, yeah, maybe we need to pay that.
Yes,
Yes. Yeah, maybe it's a good chance for business. Okay, thank you.
Any other questions? I guess I sort of had one that's maybe a little bit naive, but so from my understanding, there's a couple of different types of helmets. For example, like the ones that the lugers wear in the Olympics and bicycle helmets and things are designed to sort of explode on impact to absorb some of the energy. Have you guys, because that's fundamentally different than the types of helmets where you have the hard outer shell that are made for repeated impact, like football helmets and so on. Have you guys modeled the sort of the other style?
No, we made it because the sponsor was very only interested in the football area.
Yes, okay. That's a good reason. As good as any.
Yeah, so that's why we focus on the football
sure.
helmet. Yeah.
Sure. Okay. All right. Well, if there are any other questions, I'm sure that you can stick around and ask later. Anyone who hasn't signed the